high school students find electricity difficult. And that's completely understandable because most of what's happening in those wires is completely invisible. Which is why, as teachers, we love to give them a really tactile, tangible model they can work with to help them develop their understanding. Now, of course, you can use analogies like going to the bakery and picking up some bread, and that gives you energy to go around the circuit, but they tend to be just so kind of stories. What I love about a true model is that it gives students something they can imagine and then interrogate in their mind's eye and help them really understand what's going on. And so we've often used the water model, and if you saw my earlier blog, you know that I promised a version 2. Well, this is about version 6, lots of differences in it. I'll run through those, and then I'll talk about kind of how to use this to help students develop their understanding, particularly of voltage, current, and resistance, basic electric circuits. So first of all, it's a water model. We've got an upper tank, which is just a plastic container that I got from a supermarket. We've got PVC pipe, and most of it is just your standard watering system things that you can pick up from your local hardware. These are clear acrylic tubes. You could have, of course, just used the PVC tubing on a bit of timber, but I like the visibility of these clear plastic tubes. And then simply a bottom tank. Now, the electric pump that I've got acting as my battery, right, providing the energy, pumping the charge back from the, one side of the battery up into the higher potential side of the battery. I've used a 12-volt one, so look for a solar powered one rather than the mains powered ones, because what I've added in is an electric float switch here and a relay so that the pump is being switched. And of course we can mix water and electricity metaphorically, not a good idea to do it in reality. So nice and low voltage, 12 volts, so everything is nice and safe. And what's nice about that is it maintains that constant pressure as much as it can in the difference in electrical potential energy between here and here, which of course is being modeled in our version with the difference in gravitational potential energy. And these risers, by the way, they provide an opportunity for us to measure the force on the charge, the water to move at any point in our circuit. And of course the difference in electrical potential energy, more potential energy here than here, is the voltage across a component. And my two components are two valves which form as switches and or variable resistors. So that's kind of mostly how it's made. In order to get it like this, where the pump isn't having to work though, you need a one-way valve. And I searched around and bought a number of one-way valves. They all chew up too much pressure from the pump. And so what I found was the best thing is one of those glass marbles just inside some hose fittings. As the pressure pushes down, it seals and stops the water running back down. I did a little cable tie up over on the top of the marble to stop it sealing as it gets pushed up from the pump. And so now that's a lovely kind of one-way valve that works with very low pressure. And what's nice about it is that now my float switch, my relay, and my pump are kind of modeling what a battery does. If you've got your head torch turned off, the battery doesn't got to work that hard. When you turn it on, the chemistry inside the battery's got to work to maintain that difference in electrical potential energy. So let's get her going, and we can actually see, and this is what's so lovely about this, we can actually see and touch and feel and interact with the current, the rate at which the charge is moving. We can make measurements and see how there's a change in the potential difference across this. Now that I've reduced the resistance a bit, I've got a current flowing, there's less potential difference, and there's some more potential difference between here and here across this component. If I reduce its resistance, the current increases a little bit, but the voltage across that reduces. So lots of kind of things to play with in this model. What I love is that you can very easily make some quantitative measurements of current. And so simply into a container, obviously you want to then divide charge by unit time. So rather than this way, I can measure the amount of current that's flowing, and then I can change things and interrogate what might happen. The other addition to this model, by the way, is the ability to change the potential difference, change the voltage of the battery, if you like, the difference between here and here, and immediately you can see that there's less current flow, that all of my potential drops have adjusted to the new battery voltage, and if I measure my current, charge per unit time, you can already see that it's less than it was before. Make some measurements of that. So it's a really lovely model. And of course, it's great for giving students a good tactile concept of current being the flow of charge, and that is the effect. Voltage, the difference in electric potential energy, and resistance are the levers that we pull in order to generate that current. They are the causal agents, and the current is the effect, if you like. So it's really good for that, but it's also wonderful for that more sort of working scientifically idea of what do scientists do when they come up with something they think is a model. good thing to think about. I'll talk more about that in my next blog, but you can kind of see it's not that hard to make. I'll give you some instructions in the blog below, but of course if you would like to buy one of these already made because you're time poor, and let's face it, if you're a teacher and watching this, you are probably time poor, then hop onto my store and I can sell you one of these in kit form. More in my next blog.